Hey everyone, Mr. H again. Gonna do some 3.3. If there's the multiplication rule, of course, there's gonna be an addition rule. So we're going to look at that. Addition is gonna translate into an or probability, which we'll see in a minute. Okay, before we get to that, let's look at what's called mutually exclusive. Two events are mutually exclusive if they do not or cannot occur at the same time. So thinking about Venn diagrams here is mutually exclusive. There's no overlap. They can't happen together. Whereas not mutually exclusive, there is a little overlap there. They can happen, right? Like in these examples, number one, a single six-sided die is rolled. Event A is that you roll a 3. Event B is that you roll a 4. You're only rolling it once. It's one die. It cannot possibly be both a 3 and a 4. These cannot happen at the same time. This would be called mutually exclusive. Compare that to the second one. A student is randomly selected from ARC. The student is male. The student is a nursing major. Of course, this could happen at the same time because you could select a nursing major who is male. So this is not ME because there is overlap. Okay? The addition rule has to do with mutually exclusive in this way. So the addition rule for probability of A or B. So addition translates to or. It's basically this formula. The probability of A or B is the probability of A plus the probability of B. You just add the individual probabilities together, but you have to subtract any overlap, okay, if there is any. There is overlap if the two events are not mutually exclusive. But if events A and B are mutually exclusive, notice your formula is just that first piece because you would just essentially be subtracting nothing because there's no overlap. Okay, so let's see if we can make sense of this going through some examples. Number 3, you select a single card from a standard deck of 52 cards. Find the probability that the card is a 7 or an ace. So, probability of 7 or ace. Let's try to stick to that formula precisely, right? And I'm not even going to worry about mutual exclusive or whatever. So it says I got to find the probability of getting a 7, right? Plus the probability of getting an ace. But then I have to subtract the probability of 7 and ace, right? Okay, so let's try that out. Probability of 7. Right, so let's start with that. There are 4 sevens out of 52 cards. Probability of selecting an ace. There's 4 aces out of 52 cards. Now, what's the probability of selecting both a 7 and an ace on one single card? It's impossible, right? There's no card, and you can look back at that graph, the graphic of the cards. There's no card that has a 7 and an ace on it, right? So that's subtracting 0. Essentially, then these events are mutually exclusive, and that subtraction piece is just 0, so the formula simplifies. But you could always just use that main one, and if they happen to be mutually exclusive, you'll know it because they'll have a 0 there. So this is 8 out of 52. Guess I didn't give myself enough room on this handout, huh? Okay. Does that reduce? What are we supposed to do here? Yeah, reduced fraction, divide each by 2, or you could do divide each by 4 would be better, right? So 2 over 13. Okay. Part B, we're going to find the probability that the card is an ace or a club. All right. So probability of ace or a club, let's say. So I'm going to find the probability of ace plus the probability of club minus the probability of ace and club. Probability of ace, we know, is that 4 out of 52, right? How about the probability of a club? So remember, that's the suits. There's 13 of them. That's 13 out of 52. And then, did I double count? Is there any cards that are both the ace and the club? Yeah, I'm going to go back and look at it. it's an ace and a club is right there, right? The ace of clubs, okay? It's both an ace and a club, so I've got to subtract that one. Essentially, what you're doing is you're subtracting the double count. Oops. You just counted that one card twice because it's an ace, so you counted it in that first fraction. It's a club, so you counted it again in that second fraction. So subtract off the double count. 16 out of 52. Right? That reduces, but I don't have room to write. It was at 4 out of 13. Okay, so good to go. Right. Okay. Sorry, I'm trying to squeeze it in. There, did it. Okay, next one. You roll a single 20-sided die. Whoa, 20 sides on a die? Yeah, they exist. You have a 20-sided die. Find the probability of rolling a number less than 8 or rolling an odd number. Okay, a 20-sided die is numbered 1 through 20. So find the probability of rolling a number less than 8. Let's start with that. Let's do that fraction first. Probability of less than 8. That's 7 or less. 1, 2, 3, 4, 5, 6, 7 out of 20. Or plus, right? So always think of or as an addition symbol. Rolling an odd number or rolling an odd number. Odd numbers from 1 through 20. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. Sounds like there's 10 of them. I kind of with my fingers, so that should be accurate. Okay. Finally, subtract over 20. Are there any numbers that are both less than 8 and odd? Yeah, 1, 3, 5, 7. There's 4 of them. I gotta subtract those off. So 17 minus 4 is 13. 13 out of 20. Leave that as a fraction, or you could do a decimal if the instruction said so. Okay. Good to go. All right. What if we have some empirical data here, like in a little bar chart? A person is chosen at random. Probably that the respondent is in their 30s or 40s. 30s or 40s, right? What's the probability that they're in their 30s? It's 28 out of, well, what's the total number of people in the study? I don't know, but I would have to add up all of those, right? Get that total frequency on this one. Let me do that real quick. 19 plus 28 plus etc. That's 230. Okay. That's the probability of 30s. Probability of 40s is 57 over 230. And then I'm going to add those together. Notice I'm not doing any subtraction. Why is that? Because these are mutually exclusive, right? You can't be in your 30s and your 40s, so there's nothing to subtract. There's no overlap to subtract. So I'm just adding them up. What's that? 85 over 230? Common denominator. Don't change that denominator to 460 or anything crazy, right? Just 85 over 230. That's 0.370. Guess squiggly. Okay. How about older than 49? So that'll be in the 50s or 60s, right? So that's going to be the 89 plus the 37, right? I can add those together and just divide by the common denominator, 230. There's another way to write it, right? So 89 plus 37, 126. And a 230. And then do the division. 0.543. 8. Double check me on these. If I ever get anything wrong, send me an email. We'll fix it. Okay, let's try one more example. This is another two-way table with some OR questions involved. Donor is selected at random. Talking about blood type, you have the letter, and then you have positive or negative. Okay, so what's the probability that the donor has type O or type A? So notice it's impossible to have both, right? Because they're two separate columns there, type O or type A. So this is mutually exclusive. Therefore, you can just add them together. So there are a total of 184 type O's, 164 type A's, and the common denominator for both of those would be the grand total of 409 divided by the 409, okay? And that will be a 0.851. That says 851, not 7. That's a decimal. Oh, getting messy. Okay, I'll clean that up when I rewrite the notes. How about the donor has type B or is negative? B or negative? Okay, so how many people have type B? 45. How many people negative? 65. But notice you just double counted some people, because there are some people that are both type B and negative, namely 8 of them. There's 8 people in both of those categories. You just counted them twice, so you just have to subtract off that double count. Right? And then each of these would have a denominator of 409, so I'm just going to write it like this and get my final answer. So that'll do. So this is going to be 102 divided by 409. 249. Should write that a little bit better than the last one. Okay, 0.249. Okay, let's try one more. A or positive. Okay. A, we've got a total of 164 people. Positive, we've got a total of 344 people. So I'm adding 164 plus 344. But you just double counted some people. You double counted a lot of them. 139 people are both type A and positive. Subtract off that 139, do that math, and then divide by that grand total of 409, and you're good to go. That's going to be 369 divided by 409, and I'm getting a 0.902. Those are squigglies because they're approximate to 3 decimals. All right, so there's 3.3. We're getting there. Shoot me some emails with questions if you've got any. Otherwise, keep up the good work. Talk to you later.